So as John mentioned, I'm Jason Laumb, Director of Advanced Energy Systems here at the EERC. I've had the pleasure of working here for over 23 years, and it's my fault that we rehired Josh Stanislawski, so you can blame me for anything Josh does. Now, the title on my talk, Rare Earth Elements and Critical Minerals, What's Really Going On? Oh, my boss, Brian Kalk, I wasn't sure if he was asking me a question or he wanted this to be the title of my talk. So I chose it as the title of my talk. I'm going to go through some things that we're doing right here in North Dakota, at the EERC, at the University of North Dakota, that can be helpful to your industry and also helpful to our national security. Now, Chad already mentioned someone is going to put this up. You should feel privileged. I don't use this all the time. One might say I use it periodically. Don't worry, there'll be more. So every element on here that is shaded gray or blue is considered a critical mineral or critical element. Now, what makes something critical? What makes something critical is it is essential for our modern technologies, our economy, or our national security, and is at risk for a supply chain disruption. That's a lot of the periodic table that's at risk right now, right? What do we use these things in? If you have something with a battery, with an electric motor, with a cord on it, a hammer with a composite handle, you're using these things. That's a wide, broad range of disruption that could happen to our society, our economy, and our national security if we can't figure out how we are going to get domestically supplied critical minerals, rare earth elements. I'm going to walk through some of these in more specific terms. And Chad, I'd like you to note hydrogen didn't make the cut. Okay, I'm not saying it's not important. It's just not critical according to the U.S. Department of Energy. The ones with the yellow or gold, let's call it gold because we're going for gold, right? With the gold boxes on them are elements that we think have an economic basis here in North Dakota that we can extract, refine. We'd like to have the whole supply chain here in North Dakota to take these elements and minerals out and have production facilities here, right? I sure would. All of those ones in gold are ones that we think we can economically do here in North Dakota, or at least start to build a business case. Those elements are used in rare earth magnets for large motor drives, lithium-ion batteries. We find lithium in produced waters right now. We're starting to characterize all these resources that we have in North Dakota, whether it be from lignite, from shale, or from those produced waters. We're really just starting to dig into those produced waters, some of the opportunities that they may have. Carbon. Carbon was on that list. We all saw it up there in the upper right, number 12, right? Why is carbon critical? What are we doing? Well, here at the EERC, we are developing technologies to create graphite, which is this chicken wire structure right here of carbon atoms, and graphene, which is a chicken wire structure, one molecule thick of graphite that has some super properties. And we're able to do that directly from our lignite coal resources here. Well, why do you care? Why do you care about graphite and graphene? Even though Lynn Helms isn't here today, I'm going to tell you about a conversation I had with Ole yesterday. Ole, he's big on graphene. He was telling me about his new graphene thermos that he had. I said, well, Ole, that thing's great. What does it do? He said, oh, this thing here, this is wonderful. Keeps hot things hot, cold things cold. It's 200 times stronger than steel. It's tough as a diamond. It's abrasion resistance. When Lena hits me over the head with it, it really hurts. I said, well, that's great, Ole. What are you having it today? And he said, oh, it's a big day. I got 2 popsicles and a cup of coffee in there. He's big on the physics. Little elementary on the thermodynamics. That graphene and graphite can be mixed with other metals, and I'll show you a little bit later how that can be used. Can also be used in lithium-ion batteries. These are called graphene quantum dots. What can they be used in? Again, we made these, the ones on the left, the pretty blue ones, we made those from lignite. The ones on the right, we made those from bituminous coal. They can be impregnated in sensors that can be used downhole. They're used to fight cancer. They're non-toxic. People are injecting these into people's body right now for imaging. Why aren't they used everywhere, all around the world? They're expensive. If you want to buy 50 milligrams, just 50 milligrams of graphene quantum dots, it's going to cost you $285 for 50 milligrams. That's a, I'm no math major, I'm just an engineer, but that's a really big number when we start talking about tons and pounds, right? On the lower part of this image, that's what we like to call, or a researcher that makes it, Alex, you'll get to see him tomorrow on the tour, our croissant graphite, that we have had a lot of luck right now with proving it out as an anode material for lithium-ion batteries. And speaking of batteries, lithium-ion batteries are going to be booming. Whether you believe that we are going to have a surge in electric vehicles, one thing or another, there's going to be a market there, right? Why not provide that market with these materials for manufacturers to make these lithium-ion batteries? Hydrogen, ammonia, and ammonia production. Chad did really good of telling you about how hydrogen can be used. There's a big hole there. There's a hole with materials. How can it be transported? These technologies to utilize hydrogen are also going to need some of these advanced materials. Those hydrogen fuel cells could be used for distributed power, maybe out on a rig somewhere. Important for us. I told you that I was going to talk a little bit about some super materials. You can mix graphene in, right? So one of our researchers is working on taking a bulk metal powder, graphite graphene, getting this graphene coated powder, pressing and sintering it, and making what is called an amorphous metal composite. Now, an amorphous metal composite is important. Why? It's not crystalline. Crystalline things are great, right? Especially if it's a diamond, they look pretty. But they also like to fracture, especially on these planes. Now, an amorphous metal composite will bend but not break. Mixing graphene and graphite in there takes all those good properties of graphene: abrasion resistance, high strength. Remember, 200 times stronger than steel with Ole in his thermos, right? High thermal conductivity and high chemical resistance. It's a super material. Other infrastructure materials, getting the hydrogen from point A to point B. We've heard from several folks that hydrogen's a sneaky molecule, right? It likes to sneak out and go to recess all the time, but it also can be destructive to materials with hydrogen embrittlement. Some of these super alloys that we're working on can be important to fight hydrogen-induced embrittlement. For carbon storage in EOR well bores, also very useful. Our P-Core team did a study on corrosion-resistant materials several years back, and we're using that study to help inform what the needs are for that industry. We also have the capability here to do dynamic corrosion tests. We won't see this test rig on the tour. Right now it's operating, doing a 5,000 hour dynamic corrosion test at around 3,600 PSI and 750 degrees C in a high CO2 environment. We're testing coupons that look like this and stacked with these ceramic nuts, and we have this mixture flowing over them. We are testing these for a turbine manufacturer that wants to use supercritical CO2 in a turbine to avoid that energy penalty you get when you boil water to make steam. This also would have uses with pipeline testing for pipelines. We are also in the process of designing and modifying, maybe even putting a new system in that will be able to mimic downhole conditions, much higher pressure, maybe some lower temperature. We're working on that right now. We'll be able to test materials for folks such as you. Now, this is not just another pretty picture. It's not an ink test. It's not anything like that. We also have the capability to do laboratory analysis. Beth is going to show the labs tomorrow on the tour. The electron microscopes. We are able to characterize, not just visually, what could be causing corrosion on materials, but also chemically, what are these things? We can do X-ray maps, and Beth is going to show you that tomorrow. Now, this is saying 10 minutes, which means I'm out of time. But what does the future hold? What do I think the future holds for materials in North Dakota for the oil and gas industry? Well, like Niels Bohr says, prediction is very difficult, especially if it's about the future. You can attribute that to Niels Bohr or Yogi Berra. They both used it. I'm sure they did. It's on the internet. Google says it's true. But what I see is the opportunity for us in North Dakota to lead. Now, most people are afraid of opportunity because I believe it was Mark Twain that says it comes dressed in coveralls and looks like work. We're not afraid of work here in North Dakota, right? Certainly these folks in this room are not afraid of work. I see North Dakota leading the nation in the development of critical materials to produce things that support the oil and gas industry and allow you to do the things that you do day in and day out more efficiently with better, more advanced domestically produced materials, not from China. So thank you.